Welcome back, everybody, to week 2 of Chemistry at Home. This week we're going to be working on the second part of Chapter 9, which is about stoichiometry. Now, I am now working from home, so if there are any interruptions, I apologize, but my kids are all here, so I will do my best to keep that to a minimum. Now, stoichiometry, the reason we're learning about this is because chemists use this all the time. This is a really handy thing where we can predict the amount of product we're going to get. We can also know that if we want a certain amount of product, we can know how much of the chemicals to add together to get that product. So chemists use this all the time. So let's start on stoichiometry. Stoichiometry is the measurement and calculation of the mass and molar relationships between reactants and products in chemical reactions. Now, for this, we always have to start out with a balanced equation. That's why we learned about these in Chapter 8, and it was so important, because when we're doing stoichiometry, we must have a balanced equation. And we see here, I have a balanced equation. I have P4 plus 5O2 yields 2 P2O5. Now, our first type of calculation we're going to talk about is a mole-to-mole conversion. And we can see from the equation up here that I have 1 mole of P4. Remember, there's understood to be a 1 out front that we don't write. All of the coefficients we're going to now interpret as moles. That's what the coefficients mean. They are the number of moles. So 1 mole of P4 reacts to form 2 moles of P2O5. And I get those numbers, an understood 1 in front of the P4 and a 2 in front of the P2O5. I can also say that 1 mole of P4 reacts with 5 moles of O2. And there's my 5 moles right there, my coefficient of 5. And I can also say 5 moles of O2 reacts to form 2 moles of P2O5 using those coefficients out front. Now, using those coefficients out front, I can get a mole ratio. And the mole ratio is the ratio between the moles of one substance and the moles of another substance as indicated by the coefficients in the balanced equation. Oh, I stuttered there. So I wrote those ratios up here. I have a ratio in the first problem of 1 to 2. 1 mole of P4 to 2 moles of P2O5. My ratio in the second example is 1 to 5. 1 mole of P4 to 5 moles of O2. And in the third example, I have a ratio of 5 to 2. 5 moles of O2 to 2 moles of P2O5. Now, these mole ratios up here are used as conversion factors to convert from moles of one substance to moles of another. Your book also calls them a coefficient bridge. So let's look at how to do a problem converting from moles of one substance to moles of another substance. So I have the problems written out here. Go ahead and write those. I'll pause for a few seconds so you can get those down. Pause your video and write those down. So we're going to work with the same equation we had previously. P4 plus 5O2 yields 2 P2O5. And my question is, a chemist wants to produce 25 moles of P2O5. How many moles of P4 must be burned? So I start with my 25 moles of P2O5. So I write that down, 25.0 moles of P2O5. And I'm going to be using my bridge notation because we're converting. So I am going to do a mole ratio or a coefficient bridge here. I know from previously and looking at my equation up here that 2 moles of P2O5, using that coefficient out front, is equal to 1 mole of P4. Or 1 mole of P4 produces 2 moles of P2O5. Now I know I set this up right because I have moles of P2O5 on the top here and on the bottom here, so it cancels out. And I'm in moles of P4, which is what I want. So when I multiply across the top and then divide by 2, so 25 times 1 is 25, divided by 2, I get 12.5 moles of P4. Now I do want to point out here, right here, I will have this in all of my problems. This is my mole ratio. I must have this mole ratio or coefficient bridge in every single one of my problems that I do. So make sure you have that. Let's do another problem. The problem says, how many moles of oxygen were consumed by the reaction? So I take a look at this, and I'm starting out with my 25 moles of P2O5. But this time, I want to convert to oxygen. And I know that for every 2 moles of P2O5 produced, now you must have these labels. If you don't have these labels, you don't know what you're canceling out. So you must have the labels. Please write those down. 5 moles of oxygen are consumed. Moles of P2O5 cancel out on the top and the bottom. I'm left with moles of oxygen, so I know I have what I want. 25 times 5 is 125. Divide by 2, I get 62.5 moles of oxygen. Now, remember, right here is my mole ratio that I must always have. The other thing I want to point out is there are 3 significant digits in both of these answers because there are 3 significant digits here and here. I forgot to write the 0.0 on that second problem. That is important. We do not go with these numbers here because these are pure numbers. These do not count for our significant digits when we're using our mole ratio. Now, there's another way to do this problem. We could also go with our answer here. So I could start with 12.5 moles of P4. And I know that 1 mole of P4 always reacts with 5 moles of oxygen. So there's my mole ratio that I've been talking about. That I always have to have in these problems. And when I multiply across, 12.5 times 5 is 62.5 moles of oxygen. So whichever way I do this problem, I end up with the same answer. I just want to point that out, that there are many times multiple ways to approach these problems. Now that I've shown you how to do these, I want to take a look at the problems on page 236, 1A and B in your book, and walk you through those. So, problem 1A. They give you a balanced equation. It says the reaction that occurs when iron rust is shown below. 4Fe, so 4 iron, plus, so 4 moles of iron plus 3 moles of oxygen gas yields 2 moles of iron 3 oxide. And question 1A says, how many moles of rust? Oh, I forgot, didn't I? I usually show you the answers first. Sorry, guys. Here are the answers before I get too far into that problem, so that if you don't need to watch me do the whole problem, you don't have to. So go ahead and pause your video and check your answers. All right, so back to the problem. So the problem says, how many moles of rust can be produced from 3.2 moles of iron metal? So I have 3.2 moles of iron. And looking at my balanced equation, I want to go to moles of rust, iron oxide. I know that 4 moles of iron will produce 2 moles of iron oxide. My moles of iron cancel out, so I know I set the problem up properly. And when I multiply across the top and then divide by the bottom, I get 1.6 moles of rust. For part B, my problem asks, how many moles of oxygen will be consumed in this process? So I'm going to start with my 3.2 moles of iron again. And I know that 4 moles of iron will react with 3 moles of oxygen. So I know I set it up properly because I can cancel those units out. And so when I multiply across the top and divide by the bottom, I get 2.4 moles of oxygen gas. Now, you could have done this a different way. So the other way to do this problem would be to start with your answer from part A and say that 1.6 moles of iron oxide. Now, I know that in order to produce 2 moles of iron oxide, 3 moles of oxygen must be consumed. Oh, don't forget to write moles, because what if it was grams? Okay, that's why our units are important. So I multiply across the top, divide by the bottom, and I get the same answer, 2.4 moles of oxygen. So you could do that problem either way. You now can do your homework, which is page 241, question 22, parts A and B. And I will be back tomorrow with how to convert from mass to moles and from mass to mass. So I hope you're finding these helpful, and I hope you're staying safe and getting together with friends on social media and talking to them, but not face to face. So I'll see you later. Bye.